All right, we got another linear algebra question here. I like this question because you can answer it really quickly, but also because you can answer it several different ways, and kind of exploring those different ways that you can answer it can really help tie together some key concepts of linear algebra that you'll need for this test. So first, just the solution. Just staring at this matrix, you might recognize that it's an upper triangular matrix, and that's because all the entries below the diagonal are just zeros. So if any of the entries on the diagonal are zero, this matrix won't be invertible. I'll talk about why in just a sec. But if you come to that realization and you recognize that x are complex numbers, you might be able to just look at this and tell there's four solutions. Right? 1 plus x equals 0 tells you x equals -1. 1 plus x squared equals 0 tells you that x squared equals -1. So x is plus or minus the square root of -1. In other words, x is plus or minus I. And then finally, 1 minus x equals 0 tells you that x is equal to +1. We've got four distinct solutions. What, the fourth roots of unity, I suppose? The answer to the question is E. But how did we know that when we have these upper triangular matrices, turns out it works for lower triangular matrices too, that any zeros on the diagonal will make the matrix non-invertible? Well, it's really useful to know that there's lots of different equivalent criteria to a matrix being invertible. And I think it's worth highlighting a few of those criteria. The first one that I think is the most intuitive is that your square matrix can only be invertible if it has full rank, aka a nullity of 0. The rank is the dimension of the image, the nullity is the dimension of the null space, and the rank plus the nullity, as we talked about in the last video, is always equal to the dimension of the domain, n for an n by n square matrix. So think about what would happen if one of the entries on the diagonal were 0. It doesn't matter which one you pick. Maybe I'll pick on this guy right here. Suppose this is a 0. Well, then I could do elementary row operations to get this guy into reduced row echelon form and use this entry to knock out this entry. What I'm saying is I could create a row of zeros. If I create a row of zeros, I have a free variable. So I'd be mapping three-dimensional space onto a subspace of dimension at most 2. And that's problematic, right? If I call this matrix A, if A takes a three-dimensional space and maps it to a two-dimensional space, A can't possibly be invertible because A inverse would have to take a two-dimensional space and map it to a three-dimensional space. But that wouldn't make sense because this transformation would not be well defined. Loosely speaking, you can't have more outputs than inputs because no one input can get mapped to more than one output. Think the vertical line test in a pre-calc 1 class. So because this transformation would not be well defined, this transformation can't possibly be invertible. Another argument that you can make is that a matrix is invertible if and only if the determinant of that matrix, I guess we're calling the matrix A, does not equal 0. An easy way to remember that is when you're calculating the inverse of a matrix, you need to scale by 1 over the determinant of that matrix, right? And then you multiply by, what is it called? The adjugate, I think, of the matrix A. But ignore this part, stare at this part. If we're going to scale by 1 over the determinant of A, it's important that the determinant of A is not 0, because if it were 0, we got 1 over 0 and all hell breaks loose. When you have an upper triangular matrix, the determinant is always just the product of the entries on the diagonal. I'll talk about why that's the case in just a sec. But since this is true, the minute we got a 0 on the diagonal, even if we don't want to think in terms of the rank and the nullity, we can just recognize that 0 times anything would be equal to 0, the determinant would be equal to 0, no inverse. Okay, cool, but why is the determinant of an upper triangular matrix always just equal to the product of the entries on the diagonal? I'm glad you asked, or maybe you didn't. So there's this cool little algorithm for determining determinants. It's weird to say. I'll illustrate it for a 4x4 matrix, but it works for any n by n matrix. So I got this matrix, maybe I'll call it T. It's 4x4, so I'm pretty intimidated by trying to figure out its determinant. Fortunately, I can express this determinant as a linear combination of 3x3 determinants. All I gotta do is pick any row or any column. It doesn't matter which one. Let's say I pick this first column here. I take the first entry in this column, A, and I multiply that by the determinant of the matrix that I would get if I ignored all the entries in column 1 and row 1. Looks like that would be the matrix FGH, JKL, and OP. I've taken care of the first entry. Now I move down to the second entry because remember I picked the first column. You have to remember to alternate signs. So now I want to subtract B times the determinant of a 3x3 matrix, specifically the 3x3 matrix that I would get if I ignored all these entries. So EGH, IKL, MOP. I continue to alternate signs as I work my way down the column. So I'm going to add C times the determinant of this 3x3 matrix, and then finally subtract D times the determinant of my last 3x3 matrix. And you're like, yeah, cool, but you still need to figure out the determinants of these 3x3 matrices. No problem, we can just do the same thing again. I'm not going to illustrate all of them, but for example, if we wanted the determinant of this 3 by 3 matrix right here, just pick any row or column, it doesn't matter which one. Just to mix things up, maybe I'll pick the second column this time. Note that when you pick an even numbered column, you start with a negative instead of a positive. So I'd get negative I times the determinant of the 2 by 2 matrix that I'd get if I ignored all the entries in I's row and column, GHOP, plus K times the determinant of EHMP, minus L times the determinant of EGMO. Since we know that the determinant of 2 by 2 matrices is just the difference in the products of their diagonals, so in this case EP minus MH, in theory we could apply this algorithm to figure out the determinant for a 4 by 4 matrix. You might argue that that would take you forever, and I'd agree. However, back to our problem here, when you have an upper triangular matrix, the first column has a bunch of zeros below the diagonal. So if we pick on the first column to apply our algorithm, we'd get 1 plus x times the determinant of the 2 by 2 matrix that appears when we ignore row 1 and column 1. So 1 plus x squared, 0, negative x, 1 minus x. And then to that we want to subtract 0 times the determinant of some other matrix, but 0 times the determinant of any matrix is just 0. All right, this 0 corresponding with this 0, and then add 0 times the determinant of some other matrix for this 0 here. But again, 0 times just makes it go away. So the determinant of this 3 by 3 matrix is just 1 plus x times the determinant of this 2 by 2 matrix. But due to the fact that this was an upper triangular matrix, there must be a 0 in this position. So when I take the difference in the product of the diagonals, I really just get the product of this diagonal. What I'm saying is, due to the fact that we have zeros below the diagonal, this algorithm down here simplifies really nicely and turns into just the product of the numbers on the diagonal. If this were a lower triangular matrix, you can do the same argument if you pick the first row instead of the first column. Maybe you could convince yourself that this would work for any upper triangular matrix, not just a 3 by 3 one. For example, had this been 4 by 4, these are all zeros. So I'd get A times the determinant of this matrix. But because this was upper triangular, this would be upper triangular. And as we've already seen, the determinant of a 3 by 3 upper triangular matrix is just the product of the entries on this diagonal. So it'd be this A times this FKP. So instead of thinking about a 0 on the diagonal would make the matrix not be full rank anymore, we can think about any 0 on the diagonal would make the determinant equal to 0. And either you just memorize that if the determinant equals 0, it can't be invertible, or you think about what the inverse would be and how a 0 determinant would cause you to divide by 0. I'm sure there's lots of other ways you can come to the same conclusion, but I kind of feel like that's enough for this video. We answered the question and we tied together some key ideas and hopefully gave you a way of remembering why these things work the way they work.